Right, let's get started. Okay. So Tuesday we started the vector. Let's recap. Yeah, it was the chapter 1.3, vector equation. So we start with the definition of the vector. The vector is column vector. I mean the one column matrix was called the vector. So vector W is W is consisting of the W1 and W2. W1 and W2 are any real numbers. Instead of the whole vectors with the two entries is denoted R2. Adding vectors and scaling vectors is very easy and straightforward. And by using this, we can do similar arithmetic formulation operation on a vector domain. We also discuss how to represent your vector in a geometric manner as a point or the arrow. And also we discuss how to represent your u plus v, vector u plus v in a geometric field. So when you consider the first entry as a one axis, second entry is another axis. In our two cases, u plus v, vector u plus vector v is going to be the first vertex of the parallelogram, whose vertex defined by u0 v. 그래서 이렇게 된다는 거 이겠죠? Okay. So what about high-dimensional space, high-dimensional vector space? What about vectors in R3 or even in Rn, where n is larger than 3? First of all, vectors in R3 3 by 1 column matrices with 3 entries, x1, x2, x3, right? Which are represented by point in a 3D coordinate system. So when you consider x1, x2, and x3 are 3 elements in a R3 vector, so one of the vectors in this R3 space is going to be the point or the arrow in 3-dimensional space. Compared to the 2-dimensional space in R2 space, R3 space is going to be the 3-dimensional space. What about this? If we consider the R3, R4, or R5, it should be 4-dimensional space or the 5-dimensional space. There are ways to represent this high-dimensional space, but it's going to be really challenging to draw every time you want to, every vector you have, right? It's going to be really challenging. So please imagine what kinds of shape of the R4 or R5 space. Anyway, if n is a positive integer, Rn, read Rn, just Rn, 그쵸? Rn denote the collection of the whole list of or ordered n tuples of the n real numbers. Usually written as n by 1 column matrix, such as the vector u is equal to u1, u2, 2, un, like this. This is general formulation of the our vector in Rn space. We usually represent vector u in Rn space looks like this. In Rn space looks like this. This is the definition of the vector Rn, vector in Rn. So algebraic properties of Rn is really similar to the scalar case. I mean, when you just to substitute these vectors as a scalar value, for example, like 1, 2, 3, 4, in R space, R1 space, exactly, right? Following algebraic properties still satisfy. In other words, vector arithmetic properties are exactly same, not exactly the same, but almost the same to scalar algebraic properties. First of all, vector u plus vector v is equal to v plus u. You can easily prove this concept. Looks like this. Okay, For example, you have a vector 1, 2 plus negative 1, 1, then which is equal to negative 1, 1 plus 1, 2. It's very easy, right? And u plus v plus w is equal to u plus bracket v plus w bracket, right? This is called the 결합 법칙 in Korean, 그렇죠? 우리 스칼라에서 했던 것처럼. So you can easily prove this one as for example, u is equal to 1, 2, v is equal to negative 1, 1, then plus, okay, let's say w is equal to 3, 4, 3, 4, then it's going to be 1, 2 plus negative 1, 1 plus 3, 4, okay, right? Similarly, u plus v. In this case, v is the zero vector. Zero vectors mean the vector consists of the zeros, whose size is same as the vector u. Size of vector u. So this is the zero vectors. Anyway, u plus zero vector is equal to x zero vector plus u is equal to u is sum, right? It's very straightforward. One more thing is that u plus negative u is equal to negative u plus u is equal to 0, right? And c times u plus v is equal to cu plus cv. cu plus cv. 이거 한국말 뭐라 그러더라죠, 이거? 이거를 분배 법칙? 분할 법칙 in Korean? Who knows? 분배 법칙이라 그러나? 그쵸? 우리 스칼라 벨트 분배 법칙 맞아. 분배 법칙이죠? 그쵸? 뭐예요? By multiplying each element on the summation u plus v, which is going to be the cu plus cv. For example, 3, 1, 2 plus negative 1, 1 is equal to 3, 1, 2 plus 3. For example, negative 1, 1. Similarly, this color, c plus d times u is equal to cu plus du. By the way, c and d are scalar value, u, v, w are vector in Rn space. Okay? 그렇죠? 요거 알아야 되죠? Okay. And c times du is equal to cd times u. Very easy. Very intuitive, right? 1 times u is equal to u is sum. U is sum, right? These four kinds of properties are relevant to the summation. These four kinds of things relevant to the multiplication of matrix. How to prove? We already do this, but let's generally prove these properties. Okay, for example, we have a vector u in Rn space. For example, u1, u2, un, and vector v in Rn space as well. v1, v2, vn, and u plus v is equal to 뭐예요? u1, u2, un plus v1, v2, vn, which is equal to u1 plus v1, u2 plus v2, blah blah, un plus vn. 잘 보이죠, 여러분? Which is equal to v1, v2, vn plus u1, u2, un. So which is equal to v plus u. Very easy. Another example. CU plus V is equal to CU plus CV. Let's just write that. U1, U2, UN plus V1, V2, Vn is equal to C U1, V1, U2, V2, UN, Vn, which is equal to C U1 plus V1, C U2 plus V2, because they are whole scalar values, so algebraic scalar algebraic properties are satisfied here, right? So it's not a vector in this case, 그렇죠? 그냥 이건 지금 스칼라에서 움직이니까 당연히 우리가 알고 있는 법칙들 그냥 쓰는 거죠, 그렇죠? 그리고 이게 바로 CU1 plus CV1, CU2 plus CV2, blah blah blah, CUN plus CVN, and which is equal to CU plus CV, right? It's very easy. So CU plus V. That's it, right? Similarly, you can prove the whole of the algebraic property of the RL space for this doing yourself. You don't need to submit this homework, this kind of homework, but I strongly suggest you please do it yourself. It's really important. So 이거 한번 해봐요. 어렵지 않으니까. Okay. One more concept here is the linear combination. Linear combination. Okay. In lecture 2, we discuss linear equation. Linear equation. What's linear equation? What's linear equation? 자, question. What was the linear equation? Linear combination of the variable x1, x2, and x3, right? 그렇죠? 맞죠? Linear equation. What was the linear combination? What is linear combination? Definition like that. Given the vector v1, v2 to the vp in Rn space, given scalars c1, c2, cp. Oh, by the way, scalar we can think of scalar is just in R space, 그렇죠? Or R1 space, 그렇죠? R1 space 사실 스칼라 볼 수 있어요. 하나니까, 그렇죠? Anyway, given the vectors and given the scalars, the vector u defined by vector u is equal to c1 times v1 plus c2 times v2, blah blah blah, cp times vp, which is called a linear combination of v1, v2 to vp with weight c1, c2, cp. This is the definition of the linear combination, right? It's very easy. When you think of this is just a variable x1 or x2, this is going to be the linear equation, but in terms of the vector, this is a linear combination. One more thing is that the weight in a linear combination can be the any real numbers, including zero, any real numbers. For example, y is equal to root 2 v1 plus 1/2 v2 plus 0 times v3 is still linear combination of the v1 and v2 and v3. Okay, this is a linear combination. For example, A1 looks like this: 1, -2, -5 in R3 space, 그렇죠? And A2 consists of 2, 5, 6 in R3 space. P consists of 7, 4, -3, and 4 and R3. Question is determine where 이거 못해요. where이 아니라 whether이죠. whether B can be generated as a linear combination of the A1 and A2. Determine whether vector B can be generated or written as a linear combination of the A1 and A2. That is, determine whether x1 이것도 왜 오타가 났지? whether 맞는 말이겠네. 아무튼 whether weight x1 and x2 exists such that x1 times vector A1 plus x2 times vector A2 is equal to B. If above vector equation has a solution x1 and x2 which satisfy this vector equation, we can say that vector B generated as a linear combination of A1 and A2, right? If x1 and x2 exist, right? So the question is, find out the x1 and x2 satisfy this equation, right? So let's do that. How can you do that? Okay. In other words, in this case, this problem is reformulated to find the solution of this vector equation. So how can you do that? Because we already know A1 and A2 and P, we can rewrite this matrix, this equation. So by using the application of the scalar multiplication and vector addition to rewrite the vector equation. 그렇죠? 우리 arithmetic 하는 거 뭐 너무 당연히 똑같다고 했죠? 같았으면 이렇게 쓸 수 있죠. 그렇죠? Which is same as x1, negative 2x1, negative 5x1. 그렇죠? 띵띵띵 이렇게 했죠? 그다음에 2x2, 5x2, 6x2 from here. And 7, 4, negative 3. And by using vector algebraic property, this one is going to be x1 plus 2x2, negative 2x1 plus 5x2, negative 5x1 plus 6x2, which is equal to 7, 4, negative 3. Right. What is that? 뭐예요 이거? Linear system, right? This is a linear system. This problem reformulated as a solving the linear system, right? Looks like this, 그렇죠? 이러한 linear system을 푸는 문제로 그냥 바뀌어버렸죠, 그렇죠? Okay, let's solve linear system by 뭘로 풀 수 있어요? By which solution, which solver do you have? 자, 우리 뭐 배웠죠? 저번 시간에 how to solve your linear system, arbitrary linear system, 가우스 졸단. 그쵸? 근데 우리 수업에서 뭐라고 했어요? 가우시안 엘리미네이션이라고 안 하고 로우 리덕션 알고리즘. 그쵸? 이렇게 했었죠? by 로우 리덕션 알고리즘으로 솔루션을 풀어보자 라는 문제로 됐죠. 그렇죠? 자, let's do that. 자, 여기가 일단 우리가 equation 2라고 할 거예요. 이제 뒤에서 설명하기 위해서 equation 2. The vectors on the left and right side of the equation 2 are equal if and only if their corresponding entries are both equal. We already discussed this one. 그렇죠? 뭐예요? This one should be same to this one. This one should be same to this one. This one should be same to this one. Corresponding entries, right? 아, 이걸 물어봤던 친구가 예전에 있었는데. If and only if. What is the meaning of the if and only if? Right? This statement should be true and reverse statement should be true. In this case, we say that if and only if. 그렇죠? 그래서 뭐예요? 앞에 있는 문장. 자, 이게 A 문장이라고 하고 이거를 B 문장이라고 하면 B, A to B should be same while B to A should be same. In this case, we just say that if and only. Okay? 이렇게 많이 말이에요. 뭐 혹시 궁금한 친구들? Anyway, that is x1 and x2 make the vectorification. 요거 vectorification이었어요. 이거가 1이라고 할 거예요. 이게 1이에요. vectorification 1. x1, x2 make a vectorification 1 true if and only if x1, x2 satisfy following system. Following system. This one. 그렇죠? 결국에 이러한 리니어 시스템을 푸는 문제로 가버렸죠. 그렇죠? 자, let's do that. To solve this linear system, we will row reduce augmented matrix of the system as follows. Why? To use row reduction algorithm. So, first of all, what is augmentation? Augmented matrix of this one, this linear system. 뭐예요? What is augmentation matrix? 1, -2, -5, 2, 5, 6, 7, 4, -3. 그렇죠? Right? 그렇죠? Here, original matrix. Then let's row reduce. So to row reduce, we have three kinds of operator, 그렇죠? Which was called elementary row operations. What's that? Three kinds of things. 뭐였어요? 우리 세 가지 elementary operation. What are the three kinds of elementary operation? Row operation, replacement, interchange, and scaling, right? To make what? To make REF form of the original matrix, which was unique, right? REF form, like this. Okay, how can I do that? Let's work pivot by pivot, 그렇죠? So first of all, okay, we want to make this one as a pivot position. So we have to eliminate this term as 0, 그렇죠? For the REF form. Okay, so first of all, this is R1 and R2 and R3. First of all, to eliminate this one, new R2, it's going to be R2 plus 2R1. And R3, it's going to be R3, previous R3 plus 5R1. Then we achieve this. From now on, I wouldn't solve line by line because it's going to be very time consuming. So please do it yourself after class. Okay? 이거 이제 여러분들 이렇게 써주면 이게 이렇게 나오는 건 사실 단순 계산이죠. 안 할 거예요. 이제 여러분 당연히 이제 이렇게 나오면 생각하고 넘어갈 거니까 if you're not fully understand yet, please recap. 그렇죠? By the way, we have a first homework which is announced in Blackboard in assignment tab. Please check that, which is due on next Thursday maybe. Yeah, next Thursday, 5 p.m. Okay. 그래서 이제 여러분 요 관련해서 우리 숙제 있어요. 숙제 처음 나갔습니다. 그래서 여러분들 한번 숙제도 열심히 풀어보시고 다음 주 목요일 5시 전까지 제출하시면 돼요. 블랙보드. 맞죠? Okay. The next thing is that we want to make this one as another pivot position. So for REF form, we want to make this value 9 to 1. Then how can I do that? R2, new R2 is going to be the R2 over 9. Then new value is going to be 1, 2. Then 3, R3, to make, 그쵸? 여기까지고, 그 다음에 to make this one as a 0, new R3 is going to be previous R3 minus 16R2. Then we achieve this one. So our REF form here 1, 0, 0, 0. One more thing is that here. So to make this one as a 0 again, new R1 is going to be the R1. R1 minus 2R2. 그렇죠? Then we achieve here. So 1, 0, 0, 0, 1, 0, 3, 2, 0. So this is REF form. So what is the solution of this case? It's very straightforward, right? X1 is equal to 3 from first law, X2 is equal to 2 from the second law. 뭔가 이상한데요? 맞죠. 그죠. X2 is equal to 2, X1 is 3, right? So in this case, P is a linear combination of the A1 and A2 with weight 3, 2. X1 is equal to 3, X2 is equal to 2. In other words, P was 7, 4, 3 is linear combination of X1, 3 times A1, 1, -2, -2, -5, plus 2 times 2, 5, 6. Okay? This is the linear combination of the vector A1 and A2. Okay? Question. Question? No? No? Okay, let's continue. Now, observe that original vector A1, A2, and B are the columns of the augmented matrix that are low reduced, right? So let's go back to the problem. A1, A2, AP. Here, 그렇죠? A1, A2, AP, P are the columns of the augmented matrix that we low reduce. We want to low reduce. Looks like this. Then we can write this matrix in a way that identify each column. Looks like this. 자, 조금씩 감이 오죠? So A1 was the A1 in our R3 space, A2 was our in 3 space, P also in our R3 space, right? Then we can make an augmented matrix by placing each column vector to the corresponding column position. This is the augmented matrix. Augmented matrix, the linear system by formulated by A1, A2, and B. In other words, a vector equation x1 a1 plus x2 a2 blah blah xn and an is equal to p. This kind of linear system, vector equation, has same solution set as linear system whose augmented matrix is a1, a2, an, and p. In other words, solution of this linear system and this vector equation is same. In other words, okay, so if the solution of this augmented matrix x1, x2, blah blah xn, then this solution is going to be the solution again for the above vector equation. Okay, so that's it. In particular, it can be generated by linear combination of the A1, An, if and only if there exists a solution to the linear system corresponding to the matrix above. In other words, okay, if there is a solution of a linear system, this one, if this system has a solution this linear system probably it doesn't necessarily mean linear system always has solution, right? So if this system has a solution B can be generated by linear combination of the A1 and A2 and AN. In other words, if B can be generated by linear combination of the A1, A2, and AN, then this system has solution. This system has solution. So these two representations are exactly same, but in different form. 오케이? 그래서 무슨 얘기 하고 싶은 거냐? 자, 똑같은 얘기죠. 우리가 지금까지 배웠던 어떤 리니어 시스템이라고 하는 건 사실 리니어 시스템이라고 하는 거를 어떤 어그멘티드 매트릭스로 표현을 했었죠. 근데 그때 어그멘티드 매트릭스의 벡터, 컬럼 벡터들을 우리가 이렇게 벡터 이퀘이션을 표현하면 이렇게 될 거고, 그 말은 뭐예요? 어그멘티드 매트릭스의 each 컬럼 벡터를 가지고 벡터 이퀘이션을 만들면 그 벡터 이퀘이션의 솔루션과 그 원래 리니어 시스템의 솔루션이 같다라는 거예요. 조금씩 어려워지죠? Why? Why do we have to know this kind of concept? We already know how to solve the linear system in augmented matrix form, but why we need the vector equation? Because more efficient and effective solvers can be derived in vector equation, not an augmented matrix form. That's why we have to know the different kinds of representation of the same linear system. 그렇죠? 그게 뭐예요? 우리가 같은 리니어 시스템을 뭐 어그멘티드 매트릭스 표현해가지고 풀면 되는 걸 배웠는데 왜 굳이 그게 벡터 이퀘이션이랑 똑같다는 걸 계속 하고 있느냐? 결국에 벡터 이퀘이션으로 풀 수 있을 때 더 깔끔하게 또 빠르게 풀 수 있는 솔루션들이 있기 때문인 거예요. 단순히 그거예요. 결국에 이 두 개는 똑같은 얘기인데 다른 레프렌테이션이다 라는 걸 이해해야 된다는 거죠. 어렵죠? 어렵지 않죠? Question. 자, 우리 오늘 한번 30분 정도 지났는데 질문 한번 봐봅시다. Question so far. Or comment. Are you following now? 여러분들 잘 따라오고 있죠? 네. 교수님 행렬을 벡터로 바꿨을 때 벡터를 바꿨을 때 어떤 쓸모가 있나요? 잠깐만요. 행렬을 벡터로 바꿨을 때 어떤 쓸모가 있나요? 의의는 없어요. 그냥 another representation이에요. 행렬을 벡터로 바꿨다고 표현하면 안 돼요. 그냥 벡터예요. 그러니까 행렬도 그러니까 벡터도 행렬이에요. 무슨 행렬이냐? number of column이 1인 행렬을 그냥 벡터라고 하는 것뿐인 거예요. 바꾼 게 아니에요. 그냥 다르게 부른, 그러니까 우리가 편의를 위해서 그냥 그 컬럼만 있는 행렬을 벡터라고 표현했던 것뿐인 거예요. 알겠죠? 편의를 위해서요. 선아 학생 질문이 벡터 이퀘이션, 리니어 컴비네이션, 리니어 시스템 등 여러 가지가 헷갈리는데 정리해 줄 수 있구나. 자, 우리 한번 정리해 갈까? 여기까지 왔으니까 자, 여러분들 좀 헷갈릴 만한 게 오케이. 리니어 이퀘이션, 리니어 시스템, 리니어 컴비네이션, 그쵸? 다 써볼까? 여러분 헷갈릴 만한 단어가 리니어, 오케이. Let's summarize what we've done so far. Linear equation, linear system, linear combination, and vector equation까지 왔죠? 그쵸? 굳이 정리를 해보자면 linear equation was the linear combination of the variable, 그쵸? scalar y is equal to c1 x1 plus blah 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 cn xn. It was the linear equation, and the set of the linear equation, 그쵸? The set of the linear equation x1 x1 c11 x1 plus xn C1n xn blah 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 y m c m1 xn blah 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 c mn xn looks like this. It was the linear system. Thus, set of the linear equation. 그렇죠? 리니어 시스템 그랬죠? 이거보다 리니어 이퀘이션보다 큰 범주였죠. 굳이 표현하자면. And linear combination means we will talk about in a vector form from now on. Vector y is equal to a1 x1 vector plus an x n, right? This is the linear combination. Comparing to linear equation, from now on we will talk about in a vector space, right? Then what is vector equation? This is a vector equation. Okay? 됐지? 알았죠? 어렵지 않죠? 선호 학생? 오케이. 자, 형주 학생 2304 벡터는 R3인가요? 네? 뭐예요? 2304? 2304? 오케이. For example, you mean 2304 looks like this, right? So in this case, which is vector in R4 space, right? Okay, 그렇죠? Because there are 4 kinds of elements here. Is there any question? Another question? 자, 어렵지 않죠? 봅시다. 오늘 해야 될 게 많은데. 자, okay. If you follow well, we will introduce a very, very important definition here. Span. So, if vector v1, vector v2, and vector vp are in Rn space, n-dimensional vector, then the set of the whole linear combinations of the v1, v2, and vp is denoted by span of v1, v2, blah blah vp, and which is called subset of the Rn spanned by v1, v2, vp, or generated by v1 and v2 and vp. That's very, very important concept. Definition. Span. In other words, span of v1, v2, and vp is the collection of the all vectors that can be written in a form C1, V1, C2, V2, CP, VP with the C1, CP scalars. What is that? Linear combination of V1, V2, VP with weights C1, C2, CP, right? In other words, whole possible linear combination of V1 and V2 and VP are called span of V1, V2, and VP. In other words, from now on, we can write span of V1 and V2 and VP to represent collection of a whole possible vector that can be written in a linear combination of V1, V2, and VP. This is a span. This is span. This is span. Asking whether a vector B in span V1, V2, and VP amount to asking whether vector equation C1 V1 plus C2 V2 CP VP is equal to B has a solution which is equivalent asking whether the linear system with augmented matrix V1, V2, VP, B has a solution. Okay, wait. 자, let's go back to here. Here, we say that vector equation has same solution set as the linear system whose augmented matrix looks like this, right? In other words, from now on, we can say that span means a linear combination, right? So in other words, vector B is in span of V1 and VP and V2 and VP, which means V is linear combination of V1, VP, looks like this. Right. If vector B is in span of V1, V2, and VP is equivalent to whether vector equation, this vector equation has solution, which is equivalent to this linear system with augmented matrix looks like this has a solution. Okay. In other words, okay, it's very, very important. In other words, okay, let's suppose that you have arbitrary matrix A in augmented matrix form. 그렇죠? Here, okay, let's suppose that you have augmented matrix A, in previous lecture, we want to determine that this augmented matrix, this linear system with this augmented matrix has solution or not, or solution exists or not, right? But by using the vector, in this case the column vector, 그렇죠? V1, V2, blah blah P, we can do the same thing within a vector domain. V1, C1 plus C2, V2 plus CP, VP is equal to P. The solution problem can be applied to the same vector equation by column vectors of the augmented matrix. This question can be equivalent to vector B in span of V1, V2, VP. These three statements are whole equivalent. Question. 자, let me give you 1 minute to understand what I've done so far. 자, 1분 줄 테니까 여러분 한번 제가 지금 이렇게 설명했던 거 한번 천천히 생각해봐요. 자, 어떤 리니어 시스템의 어그멘티드 매트릭스가 이렇게 생긴 폼으로 나온다는 거는 우리가 여기서 솔루션 하는 거 뭐 리젝션 알고리즘 열심히 했었죠. 근데 그렇게 솔루션을 푸는 거는 사실 그 어그멘티드 매트릭스의 컬럼들이죠. 그냥 컬럼들을 이렇게 벡터리케이션으로 표현을 하는 거와도 똑같은 얘기인 거고, 지금까지 얘기했던 걸로 치면 그건 사실 이 벡터 B가 V1, V2, VP, 즉 컬럼 벡터의 스팬, 즉 컬럼 벡터의 리니어 컨비네이션 표현될 수 있냐 없냐 이제 문제를 바꿨다는 거예요. 그렇죠? 뭐야? 지금까지 우리가 얘 솔루션 있냐 없냐를 하려면 뭐 열심히 로우 리덕션 알고리즘 돌리고 열심히 해가지고 마지막 로우에 0.00000 그 0이 아닌 값이 있냐 없냐 이런 걸로 사실 보고 실제 솔루션이 있냐 없냐를 사실 봤어야 되는데, 이제 이 컬럼 벡터 B가 그냥 벡터로 할게요. 벡터 B가 V1, V2, VP 컬럼 벡터들의 스팬으로 들어가느냐, 즉 컬럼 벡터들의 리니어 컨비네이션 표현되느냐 안 되느냐로 우리가 찾을 수 있다는 거죠. 자, let me give you 30 second more. 소은 학생, 스팬이랑 벡터리케이션, 리니어 시스템 모두 같나요? 달라요. 선수 달라요. 이걸 이해해야 돼요. 달라요. 스팬은 벡터들의 P개의 벡터들로 만들 수 있는 리니어 컨비네이션이고, 그렇죠? 벡터리케이션, 이렇게 생긴 벡터리케이션이고, 리니어 시스템 우리가 배웠던 거죠. 자, 다 이해했죠? 혹시 이해가 안 되는 친구? 리니어 컨비네이션과 리니어 시스템. 여기를 보면 되죠? 요거예요, 요거. 리니어 시스템과 리니어 컨비네이션은 exactly same, but different form. 그렇죠? 결국에 뭐예요? 계속 똑같은 얘기예요. 무슨 얘기냐면 요 세 개 다 같아요. But we represent same linear system in a augmented matrix form here, vector equation form here, and another statement here. 그렇죠? 다르게 표현했다는 거예요. 이해했죠? Let me please give me a comment. Do you clear? Are you clear or not? Aren't you? 자, 동인 학생, 스팸. 그럴 것 같아서 이제 다음 장을 준비했습니다. 자, what is the exactly meaning of the span? Let's think about the geometric description of the span. V. 자, first of all, let V be a non-zero vector in R3 space. Let V be the non-zero vector in R3 space. Then, as we discussed previously, this vector V represents as an arrow here, right? Then, the span V is the set of or scalar multiple of V. I mean the linear combination of V. In this case, C times V. C can be any kind of real value. For example, when C is equal to 0, the CV here, right? When C is equal to 1, just V, right? When C is equal to 2, when C is equal to 2, it should be here. In this case, 2V, right? Blah, blah, blah. Whole possible scalar combination of the vector V, it's going to be just the line in 3D space. So, let me give you another example. Let's think about the span U and V. Vector span U and V. Vector U and V are non-zero vector in R3 space with V not a multiple of U. V is not a multiple of U. If V is the multiple of U, it's just V span of V, right? So in this case, we have to assume that V is not a multiple of U. So it means that V is not a CU, right? Then span of UV is the plane in R3 space that contain UV0. For example, okay, let's suppose that U is here, vector U is here, vector V is here. Then span of UV should be C1 vector U plus C2 vector U2, right? Then by arbitrarily combining C1 and C2, you can find out any point. For example, C1 is equal to 0 and C2 is equal to 0. Then the point should be here. 그렇죠? And C1 is equal to 1, for example. C2 is equal to 0. 1이라고 합시다. C1 is equal to 1, C2 is equal to 2. It should be U plus V. U1 plus V. sorry. U1이 아니네요. 미안해요. V죠? 그렇죠? 그래서 in this case, 여기다 쓸까? 이렇게 하면 얘는 그냥 제로 벡터가 되는 거고 얘는 1, U1 미안해. 그냥 U죠? 그럼 뭐예요? 얘는 그냥 벡터 U 플러스 벡터 V니까 요점이 되는 거고, 그렇죠? C1 is equal to 1, C2 is equal to 2. New vector should be U1, 2, U plus 2V. U plus 2V니까 뭐예요? U plus 2V니까 뭐 여기 있겠죠. By parallelogram rule, 그렇죠? 그렇죠? Then by randomly picking the real number C1 and C2, we can find the whole point within this plane. So span of UV is going to the plane of UV. Span of UV means the plane in our space that contain UV0. UV0를 포함하는 요 뭐예요? 요 플레인이 이 스팬의 geometric manner예요. geometric meaning이에요. Why? Why do we have to know the span? Why do we have to know span? That's very, very important question. That's why we introduced the vector equation and concept of span like this. So let's go back to our lecture 1. Okay, let's go back to lecture 1. So I told you linear algebra, it's about solving linear system, and it's about AX is equal to B. AX equals B. 여기다 표현합시다. Linear algebra is AX equals B. What was AX equals B? What was AX equals B? Okay, so your linear system, we can represent your linear system in an augmented matrix form. For example, blah blah blah. 대표할까? For example, your augmented matrix, let's say A prime, your augmented matrix for the arbitrary linear equation, a linear system, can be represented by A and P. For example, if A prime is in n by m space, then A is the coefficient matrix of the linear system, n I m minus 1, and R n by 1. 이렇게 표현할 수 있겠죠, 그렇죠? This is the right hand side, and this is the coefficient matrix of the linear system. Right? Then solution that satisfy this linear system can be represented by AX equals B. AX equals B. Right. 그렇죠? 잘 이해해봐요, 여러분. AX equals B라는 솔루션이 결국에 뭐예요? 이걸 만족하는 솔루션이, let's suppose that solution X is equal to X1, X2, blah blah Xn. Then we can write we can write this problem in a ax equals p. ax equals p. Right? 바로 미안해. 아직 여러분 이거 모르겠구나. 잠깐만. 이렇게 합시다. 이렇게 봅시다. 여러분 아직 벡터를 모르니까 이렇게 봅시다. 자, the solution of this linear system was the vector f can be represented in a vector x in x1, x2, blah blah xn. Right? And the meaning of the solution. What's the meaning of this x and x solution? Let's suppose that this matrix A consisting of the vector v1, v2, v m minus 1, right? m minus 1. Then our linear system can be represented by v1, x1, v2, x2, blah blah. v에 m minus 1, x m minus 1 is equal to vector p. It was m minus 1. Right. And this one is a linear combination of vector v1, v2, and vm minus 1. Then it's going to be span v1, vm minus 1 is equal to p. Okay. In other words, why we have to know the span? Because our ultimate goal is to solve this linear system, right? We want to find our solution, this solution. But rather than using low reduction algorithm or Gaussian Jordan elimination, something like this, if we have the span, we can just say that we can just determine whether vector b is equal to span or not. Then we can say that this statement is true or not. We say that we can say that our system has solution or not. That's why we have to know the span, concept of span. 자, 여러분 제가 지금 좀 설명하면서 약간 횡설수설했는데 여러분들 어디까지 아는지를 제가 몰라서 설명을 해봤는데 다시 설명을 드리면 이런 거예요. 자, 이게 뭐 하는 거냐 지금. 자, 우리가 지금 뭐 하는 거예요? 우리가 리니어 알지브라 하면 뭐 하고 싶은 거예요? 요거 풀고 싶은 거예요. 어떤 리니어 시스템이 있을 때 어떤 여러분들의 리니어 시스템이 있어요. 여러분 리니어 시스템의 솔루션 X를 찾고 싶은 거예요. 우리가 하고 싶은 거죠. 그렇죠? 이번 리니어 알지브라의 4기에서 하고 싶은 게 계속 이걸 하는 거예요. 그렇죠? 근데 이걸 풀려고 했더니 우리가 지금까지 배웠던 건 뭐예요? 뭐 로우 리덕션 알고리즘 이런 걸 풀었죠. 뭐 로우 리덕션 알고리즘도 강력한 방법이긴 하지만 사실 우리는 조금 더 어드밴스드한 뭔가 우리의 도구가 필요한 거예요. 그러니까 로우 리덕션 알고리즘보다 조금 더 나은 거를 개발해 보자. 로우 리덕션 알고리즘도 충분히 좋은 알고리즘이지만 더 나은 알고리즘을 개발해 보자 라는 사람들이 고민했겠죠. 근데 그러다 보니까 이 A 매트릭스, 아우멘티드 매트릭스, 코에피션트 매트릭스 쪽에 있는 A 매트릭스를 이 컬럼 벡터들, 이 컬럼 매트릭스들을 쭉 쌓아 보면 이 솔루션을 이 컬럼 벡터랑 표현하면 이렇게 표현될 수 있겠다라는 거예요. 그럼 이게 뭐야? 아까 말한 벡터 이퀘이션이잖아요. 그렇죠? 그러고 보니까 이 벡터 이퀘이션의 왼쪽 텀이 사실 리니어 컨비네이션인 거죠. 그럼 이걸 맨날 이렇게 쓰는 귀찮잖아요. 맨날 x1, x2 어떻게 써? 그러니까 이걸 스팬으로 표현해버리는 거예요. linear combination of the x1, linear combination of the v1, v2, and vm-1. 그쵸? 그럼 뭐예요? 이게 나오는 거 무슨 얘기를 하고 싶은 거냐? 어떤 벡터 B가 span of 컬럼 벡터들, 즉 span of V1 and V2 and Vn-1에 랑 같냐 안 같냐면 결정을 내리면 우리가 솔루션이 있냐 없냐를 바로 알 수가 있는 거예요. 로리덕션 알고리즘 쓰지 않아도. 훨씬 문제가 쉬워져 버리죠. 그렇죠? 돌아가 볼까요? For example, 자, okay. So this is our augmented matrix. We want to say that we want to determine it has solution or not. It has solution or not. So to solve this problem with low reduction algorithm, you have to low reduce this one and here, this one, right? It's going to be exhaustive way, exhaustive operation or process, right? But from now on, we know span. We know span. Then span, I mean the vector V1 here, vector V2 here, and vector V3 here. Then, it's not V. 아이고. Augmented matrix였으니까 이건 그냥 B예요. 그렇죠? Then span of vector V1, V2 is equal to B or not. So we can just say that it has solution or not. That's why we have to know the span. 알겠죠? 그게 뭐예요? 우리가 그럼 span 하면은 1, 2, 5. 자, 이거의 스팬이 7, 4, 마이너스 3 이랑 같냐 안 같냐면 바로 알 수 있으면 우린 그냥 로렉션 알고리즘 쓰지 않아도 솔루션 있는지 없는지 알 수 있어요. 그렇죠? 그게 이제 우리 바로 스팬을 배워야 되는 이유인 거죠. 그렇죠? 이 스팬이 근데 결국에 지오메트릭 미닝을 또 가지고 있어요. 아까 말했던 요걸 진짜 어떤 지오메트릭 스페이스에 보여주면 이런 그림이 나오는데 이제 이게 우리가 이 챕터 마지막에 가면 이 플레인이랑 요 나중에 B가 하나로 다 엮일 거예요. 그래서 어쨌든 스팬을 배워야 되는 이유, 더 나은, 더 어드밴스드한 솔버를 가지고 싶기 때문인 거고 스팬은 이런 지오메트릭 미닝을 가지고 있다. 이게 결국에 B랑 어떻게 연관되느냐 마지막에 볼 거예요. 알겠죠? 아이고 설명 너무 오래 길게 했네. 10분 넘게 했네. 자, that's the end of chapter 1.3. 맞아요. 예담 학생 말이 맞아요. 그러니까 스팬을 더 쉽게. 자, 우리가 이번 학기 하고 싶은 거. What do you want to do in this semester? We want to solve AX equals B. We want to solve your linear system, but with more powerful and more advanced technique. So low reduction algorithm was just a simplest one, but from now we want to derive the more advanced technique to efficiently and effectively solve your linear system. That's why we have to know the span. 그렇죠? 맞아요. 예단 학습자. 그래서 스팬을 알아도 결국에 우리가 더 빠르고 더 정확하게 솔루션 스페이스를 얻어가고 싶기 때문인 거예요. 그게 이제 바로 이 챕터 1.4에서 볼 이 matrix equation AX equals B your linear system을 AX equals B로 arbitrary 표현하는 여기서 이제 요 우리가 두 번째 알고리즘을 완성시킬 거고요. 알겠죠? question. 이걸 오늘 끝냈어야 되는데 설명이 좀 길어졌네. 괜찮아요? 다음 시간에 합시다. Okay? So, anyway, this matrixification, what we want to derive from your linear system in augmented matrix form, which is the much easier solution, I mean the much easier form to understand your linear system. Okay, before that, to understand AX equals B matrixification, you have to understand what we've done so far. What is linear system? What is linear equation? What is the linear combination? What is the span? What is the vector equation? Okay, please recap before next week. Okay. 그래서 이제 여러분들이 이제 여기가 정말 이제 중요한 얘기예요. 우리가 이번 학기 내내 얘기를 나눌 과연 AX equals B는 뭐냐? matrixification에 관한 얘기를 할 거고 그걸 이해하려면 결국에 이제 우리가 오늘까지 얘기했던 것들을 완벽하게 이해를 해야 돼요. 알겠죠? 그래서 이제 여러분들 복습 잘하고 다음 시간에 보도록 합시다. One more thing is that question. R3형의 스팬이 스팬 안에 한 평면에 들어가 있지 않은 세 개의 벡터가 들어가면 좌표 공간 전체를 표현 가능하니 다 똑같은 스팬을 나타내는 건가요? 네, 맞아요. 규현쌤. 요 얘기는 이제 우리가 다음 주에 얘기할게요. So, next week we'll talk about the geometric meaning of the span and how to understand your span. Okay? Last question. 과제 있어요, 여러분. I will show you. Okay. Here's your blackboard. No, it's edit mode. Okay. Where's the stunt mode? Here. So this is the stunt mode. I mean, you can see here assignment or lecture room or lecture note. And when you see the assignment here is our first homework. So far we discussed chapter 1.1, 1.2, 1.3, right? Then, but homework 1 will cover to chapter 1.4, which is due on March 24th, 맞죠? Next Monday, 그죠? Before our Thursday class. Yeah, here's some instruction. Then, if you are a student, you can submit your homework here by yourself. You can upload homework here. So please check that. This is our first homework. Okay? 이제 여러분, 우리 첫 번째 호mework 나왔죠? 이제 요거 가지고 여러분들이 이제 열심히 복습해서 풀어주시면 됩니다. 됐죠? 자, 민준 학생 질문이 R3 이상의 스팬은 기하학적 생각할 수 없나요? 아까 말했던 거랑 똑같은 얘기예요. 그러니까 우리가 R3 이상은 사실 그리기 너무 힘들어요. 그릴 수는 있어요. 그 R3 스페이스를 여러 개, 그러니까 R3 스페이스가 여러 개 있는 폼으로 그리면 그게 R4 스페이스가 되겠죠. 굳이 그릴 수 있지만 사실 불가능에 가깝다. 사실 우리가 R3 이상에선 사실 기하학적으로 언더스탠딩 하지 않는다. 하지만 R3 이하에서 정의된 모든 개념들이 R4, R5, Rn까지 다 똑같이 정의되기 때문에 우리는 R2, R3에서 정의가 되면 충분히 쓸 수 있다라는 거예요. 자, 형민 학생, 너무 좋은 질문이고 요거 우리가 다음 시간에 보여줄게요. 스팬을 하면 어떤 좋은 것들을 할 수 있는지. 어차피 연립해야 되는 거 아닌가요? 아니에요. 안 해도 돼요. 요건 다음 시간에 알려줄게요. 됐죠? Other question? Okay, that's it. So this is the end of this lecture, and this week, have a good weekend, and let's see next Tuesday. Okay? 여러분 오늘도 수고하셨고요. 우리 다음 주 화요일 날 보도록 합시다. 고생하셨습니다.